Hi, everybody. Welcome to week number 7. Today, we're going to expand our little knowledge about nuclear chemistry, and we're going to go into the different types of decay. So we're going to build upon what we talked about last week.
All right, so first we're going to talk about the difference between ionizing and non-ionizing radiation. Non-ionizing is the lower energy radiation, so it's going to cause less damage. And you're going to recognize these. That's visible light, infrared, microwaves, and radio waves. All right, so they can give energy to molecules. They make them vibrate. Electrons can jump to higher energy levels, but they don't cause a lot of damage unless you have overexposure. Now, ionizing energy, radiation, on the other hand, is high energy. So this is where you're going to see more damage. They can actually eject electrons, which means you're going to create ions and free radicals. So you're going to see damage done to proteins in your nucleic acid, so your DNA. You're going to have, it causes an inability to heal, birth defects, cancer, and radiation poisoning. So what is nuclear radiation? Oh, Sam, this is you?
I think it's you.
Okay. So nuclear radiation, it's a form of ionizing radiation caused by changes in the nuclei. We've been started with that already, right? We have the unstable nuclei, and it's going to break down into a new element, and it's going to release energy. Radioactive decay from last week is the change in the nucleus as a result of emitting particles and energy, usually alpha, beta, or gamma. We mentioned those last week. And then there's radioactivity, and that's the spontaneous emission. So it happens randomly on its own, not started by anything else.
So we're going to do a quick review of the atom next. We're going to start with this example. It's potassium. In the upper left corner, next to the potassium symbol is number 40. This number is the mass number. That's going to give us number of protons plus the number of neutrons. In the lower left corner is the number 19. This is the atomic number and shows us the number of protons. If there was a number up in the right-hand corner, it would be the charge, and that would tell us how to adjust the number of electrons. For this example, there's 19 protons. Again, that comes from the atomic number. There's 19 electrons. There's no adjustment. There's no charge. So there's the same as the proton. And there's 21 neutrons. So I like to look at this left-hand side like a math problem. It's 40, because that's the total of both, minus 19, which is just the protons, gives us 21 neutrons. I have a couple for you to try. Go ahead and pause your video and give these a go. All right, so you should have, for these ones, for lithium, 7 is the mass number, 3 is the atomic number. So that 3 tells us protons. There's 3 protons. The charge is +1. If it's a positive charge, you have more protons than electrons. If there's no number next to it, it's assumed it's 1 plus. So there's 1 less electron here because there's an additional proton, and that net charge is +1. For neutrons, that subtraction problem, 7 minus 3 is 4. Selenium, again, the atomic number at the bottom gives us protons. The 2 minus adjusts the electrons. Now we need 2 additional electrons to get a net negative charge. So now there's 36 electrons, 2 more than the protons. And neutrons is the subtraction problem. 78 minus 34 is 44. You can try these ones as well. Feel free to pause. And you should have gotten that uranium-238 has an atomic number of 92, which gives it 92 protons. There's no charge, so no adjustment, 92 electrons. Neutrons is 238 minus 92, gives you 146. For uranium-235, it's just a little different, right? Because it's the same atomic number, so no charge again. Protons and electrons are still both 92, but the number of neutrons is different. That 235 minus 92 now gives us 143 instead. So what do we call these 2 atoms? Well, they're isotopes, which is a review from last week. And atoms of the same element, they have the same number of protons, but different number of neutrons, are considered isotopes. Remember that they share physical and chemical properties that are very similar, rather, but their nuclear properties, or what makes them, how stable they are, can be very, very different. In this case, uranium-235 is explosive and uranium-238 is not. And the pictures you're about to see are not lined up, but they're labeled correctly.
And we're just going to talk a little bit about each of the following particles and eventually lead us into array. And I'm going to pass it to Ms. Ashburn to talk about the alpha particle.
All right, so first up is the alpha particle. So this actually is a helium nucleus, is what it looks like. You have 2 protons and 2 neutrons. It has a +2 charge. And you notice it gives 2 symbols. They mean the same exact thing. It's just you can use the curly A, which means it's the alpha, or you can use He since it is a helium nucleus. So they've got the mass number of 4 for those 2 protons, 2 neutrons, and an atomic number of 2 for the 2 protons. It's the largest of the 3 main types of nuclear decay particles. It's got a weak penetrating particle. It can be stopped by paper or skin, but if you ingest it or inhale it, it can do a lot of damage. Sources of alpha particles. They're often produced when atoms with an atomic number greater than 83 decay. So that's down near the bottom. So here you're actually seeing an example of an alpha decay. So you have an element and it's going to break down into the alpha particle, and look at, now it's got a new symbol. Why? Because the atomic number has changed. What's interesting with these is if you can think about it as 2 math problems. So if you look at the 3 mass numbers, you got 226 equals, so you almost replace that arrow with an equal, 4 plus 222. Okay, and this is going to become handy when we get to part B. And then you can do the same thing with the atomic numbers. You have 88 equals 2 plus 86. Just simple math.
Beta particles is the next particle we're going to talk about. These are fast-moving electrons that are emitted from the nucleus. Because they are electrons, they have a -1 charge. And again, there's 2 versions of the symbol. So E for electron, or the curly B for beta, the Greek symbol. Since it's an electron, there's no mass, so the top number is 0. And it's going to affect the atomic number with a -1. These are 8,000 times smaller than alpha, so this leads to much greater penetrating power. However, beta particles can still be stopped by heavy clothing. During beta decay, a neutron actually decays to produce a proton and an electron. And this is going to explain why there was that funny -1 at the bottom. So this neutron breaks down into a proton and an electron. So the proton stays in the nucleus and the electron gets emitted or ejected. So for the neutron, it has a mass of 1, but no proton. The proton has a mass of 1 and a proton. And the electron has a mass of 0 and -1, because remember, like that math problem, these bottom numbers all have to equal each other. So 0 equals 1 plus -1. An example of this is lead-210. Lead-210 is, the 210 is that mass number. So again, it's that math problem. You have 210 equals 210, the mass of bismuth, plus 0, the mass of the electron that was emitted. And likewise, the atomic numbers also are another math problem. The mass number of lead is 82, and that equals the mass number, or sorry, the atomic number. The atomic number of lead is 82, and that equals the atomic number of bismuth, 83, plus that -1 from that proton and electron being emitted. So you see that electron particle there. Oops, I think I hit it twice. There you go.
And finally, we come to gamma. You're going to notice that it's not a particle, but it's a ray. So that's why you're going to notice on the first line that it has no mass. And if you look at the symbol, it also doesn't have a charge. Okay, so there's no protons, there's no mass, there's no neutrons. Okay, so it kind of looks very innocuous. It doesn't look harmful. But you have to remember, when we talked about radiation a couple of weeks ago, we know that on the right side of the electromagnetic spectrum, or on the shorter wavelength side, we're going to have waves that have high frequency and that have high energy and can be dangerous to people. So as it comes to penetrating power, gamma rays can actually go through several feet of concrete or lead before they're stopped. So does that mean can it get through your skin? Yeah. Can it get into your organs? Yeah. Do you have to worry about this? Actually, not really, because luckily here on Earth, gamma radiation cannot penetrate Earth's magnetosphere. So where do you normally see gamma radiation? Gamma radiation usually comes from stars. Remember the whole idea of stability, that we want to create products that have lower energy and are more stable. So usually the gamma rays are accompanied with a beta or alpha decay, or in the sense of nuclear fusion in a star, creating helium from hydrogen atoms. It's a way of gaining that stability back. Again, one of the things I think is really interesting about this is if you take NASA and astronauts as they went to the moon about 50 years ago, you notice that they wore very, very, very thick suits. And you're going to notice that they carried a pack. In that pack was an air conditioner. And you might be thinking, well, space is really cold. Well, in order to protect themselves from the ionizing energy from the gamma radiation, they actually had to wear a suit about 50 layers thick that alternated between aluminum and lead layering. So it was really, really heavy. They had to really protect themselves, especially before we started space travel. Scientists didn't really know how astronauts would fare once they left Earth. And again, here on Earth, you don't have to worry about this, but it's very similar to what you've seen with X-rays. If you've ever broken a bone or anything, you had to go to the dentist, you know that they actually put on a lead blanket over you to protect you from that radiation. And that kind of goes along with, hey, gamma radiation also can be stopped via lead. And you might think, well, you don't have layers and layers of lead. Well, that's also because X-rays are lower energy than gamma rays. So that's why you need less. And I'm going to throw it back over to Ms. Ashburn to finish.
All right, these are the last two particles we're going to mention, but guys, we're not going to need these for part B when you're balancing. We just wanted you to kind of see them, and that is the neutrons that can be emitted, but there's also what's called a positron. You notice it looks very similar to the beta particle, except its atomic number is 1. And just to close this out, a quick summary of the penetration powers. You'll see alpha being stopped by paper, beta being stopped by your skin. Neutron, right, is getting stopped by water, but then there's the gamma. It goes all the way through until you get to the concrete, and that's where you know the lead and the concrete barriers.
And that's where we're going to stop for now. We're not going to say goodbye, because part B, you're going to see us again in a